All right, welcome to Helicopter Pilot Study Group number 18. Today we're talking about the principles of flight. The idea behind this, or just behind the study group, is to provide a platform for helicopter lovers, students of all levels, to be able to take the opportunity to present on a topic of interest or a task from the ACS. We'll review the presentation as a group, give you our thoughts, and then talk about another task or another topic, or continue on that one depending how the thread goes. We generally talk for about an hour and a half. We meet once a week. I chose this week the Principles of Flight, Area of Operation 2 from the Commercial ACS, Task D, Principles of Flight. And I was thinking about last night, trying to fall, or not last night, but a couple nights ago, trying to fall asleep, thinking about how I'd explain that a bird flies to my niece and nephew who are young, 6, 7 years old. And I also realized that as I was going through my flight school early on, I'm not even sure I really completely understood the concept until way later. And we learn about immediately in rotorcraft world, immediately learn about the principles of flight of a helicopter, but we don't really understand the basics of what a lot of that is. And so that's what I really wanted to talk about in this was talking about what it is that make things fly. So I'm going to get started here. We see a lot of things in the sky, and we know a lot of things fly, and we don't always know why. I think as we're young and we're curious, or I asked my better half why she thought birds fly, and she said anti-gravity, and she didn't know 100%, obviously, right? But that's not actually wrong when I think about it. So we're going to talk a little bit about that. But how is it that things like this that's a flamingo flies, and the Wright brothers' first planes, like what did they figure out to make them fly? How did this Sikorsky helicopter actually get airborne and fly? How is it that a Falcon and a B-2 can, I think it's a B-2 or B-21 or something, how can they fly? They have very similar profiles. So obviously we're borrowing something from this Falcon for this bomber, right? And then how is it that kites fly? So I was just kind of running through those things, and I wanted to explain why that is. And really what it is, as this shape moves through the air, the air molecules traveling over the top of the curvature of that shape are forced to expand and accelerate significantly faster than the air underneath. And we see that in this diagram here. And this shape is called an airfoil. And it's an airfoil that is the key component to everything that flies, essentially. And airfoil is what is required to generate lift. And what happens here is, as this air is moving over the top, it's, like I said, speeding up. But with Bernoulli's principle, Bernoulli figured out and states that as velocity of a moving fluid, and air is a fluid, as that velocity increases, its pressure will decrease. So what happens is we have a pocket of low pressure sitting on top of the wing, and an area of high pressure underneath the wing, which is then pushing the wind upward into the low pressure zone. And as we know at this point, if you are a private pilot, you'll know that high pressure moves into low pressure. Think of a balloon that is blown up and under pressure. When you release the pressure of that high pressured balloon, it escapes into low pressure. So high pressure moves into low pressure. And now Newton realized that his third law is that every action requires an equal and opposite reaction. And so as the wing pushes a mass of air downward, the downwash, the air exerts an equal and opposite reaction, pushing the wing upwards. And that's how lift is generated. And that's shown here in the example. We have high pressure down below and high pressure up above, forcing lift up. Now, the Wright brothers understood this concept of the airfoil and how lift is produced early on, far more than any of their competitors. And they learned that because a lot of the competitors were using Smeaton's coefficient for air pressure baseline, which was inaccurate. However, they ran a number of tests, but nobody knew that. And they ran a number of tests. They used wind tunnels. They experimented with different shapes of wings, lengths of wings, and they were able to find what they found at that time with the technology that they had, the ideal shape for a wing to be able to generate lift. Now, in this picture here, we're seeing a glider. There is no propulsion here, so this isn't powered flight. However, wind, the relative what is required for a airfoil to take flight is relative wind over the center point, or over the airfoil. So you could have a an airfoil, which is kind of the shape of my mouse, actually. You could have an airfoil sitting there, and it's obviously not going to take flight. But if we add relative wind to the front of the airfoil, then the principles of flight start to take shape. So here is an example, right? The relative wind is the direction of the airflow relative to the airfoil that allows for lift to happen. So in the front of the wing, on the beginning of the camber of the chord line, in the beginning of the camber of the airfoil, as the relative wind pushes into that, we have the high pressure down below and the low pressure up above, and that's generating lift. No wind, no lift. And this works well with a kite, right? So if this was just a windy day and they had a number of different airfoils, you could lift a guy off the ground, and this was common practice in World War I for observations. Now, if this was towed behind a vehicle, then we would be using thrust and power to pull. If this was a non-windy day, for example, we could create our own wind by generating thrust by pulling this kite and this guy behind a vehicle to be able to get that wind over the airfoil for a lift to take place. So this is an example of what that relative wind is, how that relative wind works on an airfoil and generates lift.
And in theory, once we get the higher pressure above, there it goes, the plane should fly all the way up that circuit. Look at that. And as the wind goes off again, it will drop back down. Wind on, back up, back up. Oh, look at that. And wind off. I could do this all day.
I could too. No wind, no lift. I am going to... Craig, do you mind muting your mic?
Yep.
Okay.
Yeah.
I can do it. I got it. You're good. Thank you. All right, sweet. So we're back. So that's how the wind over an airfoil generates lift. And we don't need thrust, or we don't need power or thrust to do that, right? So birds glide. They generate thrust through their wing movement. Birds glide, gliders glide, kites fly. Those things all work without power, and you can generate lift. Now, in a perfect example of this, in the most perfect execution of relative wind on an airfoil and a wing, is this. In nature, it is done to perfection. It's fascinating. Kind of reminds me of a helicopter. But this bird's wing and that bird's airfoil, that wind is so gusty right into that bird, he can just sit in one spot, and that wind over that airfoil of the wing keeps it in place. So we have that high pressure down low, low pressure up above, Bernoulli's principle, and Newton's third law in action. So what happens when there is no wind? How do we bring an airfoil into flight? And that can be done by generating lift with thrust. So first principles, we're creating basically an airfoil on a propeller. And what we did is, and we still do, is we turn that propeller by an engine, creating lift of its own, but horizontal lift, which then propels the aircraft forward, and the relative wind work flows over the wings, then generating lift. So why all this airplane stuff? Well, I know this is a helicopter group, but we have to understand the basics of, I think, how airfoil flows over a wing to understand how a helicopter works. And so we'll talk about the forces that it is acting upon this wing during flight. So we know we have the high and low pressure. We have the relative wind flowing over our wing, right? We have low pressure and high pressure above the wing and below the wing, right? We have thrust that is then propelling the airplane forward, creating that relative wind over the wing. So we could fly an airplane on a day with no wind because through thrust we are generating our own relative wind. However, as we generate thrust, there's a component of drag. So just like anything that flows through the air, you know this in aerodynamics on your car, you know, you've heard about these things, the things that, like those big old semis from the 60s and 70s that were just essentially big flat bricks. Those things had no aerodynamics, right? Whereas opposed to a Ferrari has very smooth aerodynamics. So it's much more efficient through the air. And so drag, obviously that semi truck is going to have substantially more drag than say something like the Ferrari, right? So our drag opposes our thrust. And also, as we generate lift, we have an opposition of gravity and weight that wants to pull the aircraft down, or the flying machine or bird down. So we have we have how much lift we're generating opposed by the amount of weight that we are experiencing. So this is the same concept in a helicopter, right? Our main rotor blades generate lift opposed by weight. Our main rotor blade generates thrust, opposed by drag. So let's talk a little bit about drag because it's essential. We have form drag, which is the top here is that semi-truck blasting through Interstate 70 at 80 miles an hour, burning 50 gallons of fuel or something, right? An hour, just like ripping through fuel. As the shape of the object through the relative wind becomes more aerodynamic, it becomes more efficient. Now, induced drag is a byproduct of lift. So as we're creating lift through our airfoil, when we change the angle of attack, which we'll talk about here in a minute, basically the angle at which the airfoil flows through the air, that in itself generates drag. And a good way to think about this is, we've all done it, but when you're driving in a car and you stick your hand out the window and you create a little airplane with your hand and you make a little wing and you pitch up and the airplane flies up, and you pitch down and your wing flies down, and you do this up and down motion while you're driving in the car. That, when you lift up, you notice that it's harder to keep your arm forward. You feel the weight and the pressure of that relative wind hitting the bottom of your hand, causing it to kind of move back, right? What you're doing is creating more drag. When you straighten your hand out, it's nice and smooth. It doesn't take nearly as much effort to hold your hand that way. So that's an example of induced drag, and that's essentially the same concept that an airplane wing is experiencing as it changes its angle through the air, and as the rotor blades in our helicopters change pitch, and they feather through the air. Parasite drag is essentially form drag, skin friction from the surface, and form drag, and in interfering with parts of the airplane that aren't necessarily aerodynamic. So there's just a byproduct of flight is just drag in space. So anytime something is moving through space, it's never perfectly smooth enough to the point where drag is eliminated. We always try to get that way. You notice that there's far less rivets on airplanes. Howard Hughes was the first to kind of smooth out the airframe to make things nice and smooth to reduce parasite drag. Those early biplanes had an immense amount of parasite drag, and they were far from efficient in comparison to modern airplanes, which are really smooth and clean. And the idea is to mitigate the amount of parasite drag. And we experience the same thing on our rotor blades. There's pits. There's our rotor blades, our aircraft itself, all sorts of areas where parasite drag can kind of impede our progress. So what we know is we have these three main forces of drag that are all acting on our flight. And so what we need to understand about drag is where in this ratio is the most efficient place, because drag changes at airspeed. So we know that our induced drag, as we become more efficient and move faster, it goes down, but our parasite drag and our profile drag increase as our airspeed increases. So where is that sweet spot? And in the POH for the R44, we know our max glide ratio, which is a good kind of understanding of powered off total low portion of the total drag curve. We can glide at 90 knots and 90% RPM, and that'll be our max glide, most efficient way to get max distance with our engine off. And we know at our best rate of climb at VY is 55 knots, and that's the ideal spot in this drag to curve ratio that we can kind of put our helicopter in the right spot to maximize efficiency and get good climb. So there's another term for that. I think it's V. What is that? There's another term for it. LD max, L/D max, and that's not actually in the POH, but I did some research and I'm pretty sure it's very similar to VY or max glide. So maybe you guys can help me kind of clarify that when I'm done here. All right. So how does the angle of the airfoil into the relative wind affect the lift, right? So we know if we were at, if we had our airfoil just kind of sitting on the ground and there was no wind, we're obviously not going to pick up. But if we want to increase our lift, if we want to increase our angle as we're moving forward, we can change the angle of our airfoil to increase our lift. But there becomes a point where as we increase that angle so much that we then separate kind of the airflow and behind the top of the airfoil, and it basically becomes dirty air that is turbulent, and it's not nearly as effective at generating lift as the clean air that we have at lower angles, pitch angles. So pitch angle is a critical component not only in airplanes, because once you reach the critical angle of attack, and in most cases it's around 15, 16 degrees, that's when that wing will stall and have this turbulent wake behind it, and you're not generating lift, and you lose that component of, or gravity, and the weight starts to win in the battle between lift and weight and pull the aircraft down. And that'd be the same scenario in an airplane as in a helicopter. If we overpitch the helicopter, if we pull so much pitch or pull so much power that our angle of attack is too aggressive, then what happens? Our induced drag increases so much that our engine and our power can't keep up with it, and we start to lose lift, and our rotors will then slow down, and we can get into a number of issues. That could be a low rotor RPM scenario, but we are essentially losing lift. So helicopters have a wing. Our wing just rotates. And there's a number of different types of wings on helicopters. Most of them have two different types of wings. We have the wing on top, which is our main rotor, and we have the wing on our tail, which is our tail rotor. And these are the same concept of an airplane wing, just slightly different in their cross-section and how their angle of attack is created, because we have different lift sections on our rotor wing that as the wing spins through the air, we'll talk about all this in another lesson, but as the wing rotates through the air, each portion of the blade or the rotor blade is creating different levels essentially of lift. More lift in some cases, less lift in others. So, do you notice anything different here in the main rotor wing of a helicopter and the main wing of a Cessna? The big difference here is we have two different types of airfoils here. It's the same concept. They're both airfoils, but one is non-symmetrical and one is symmetrical. And the difference here is a asymmetrical or yeah, a asymmetrical airfoil like that we have on, or sorry, symmetrical airfoil that we have on the Robinsons, when it is at a zero angle of attack, there is no lift being generated. So this allows us to keep our helicopter in blade spinning it at power, at takeoff power, without actually taking off. We don't have brakes on our wheels like airplanes do. They have their props that are spinning and they're ready to go at all times. They take the brakes off and they're off and they're running. Helicopters don't have that luxury, right? We are just sitting on the ground. If we had a symmetrical or a non-symmetrical or asymmetrical airfoil like a Cessna, soon as we started spinning those rotor blades, our helicopter would want to move. We'd either have to pitch it way down below the angle of attack, which would push us into the ground, not ideal, or we would just essentially, as soon as we spooled up, we would take off. So that's why we have a symmetrical airfoil as opposed to an asymmetrical airfoil. And you hear about this a lot, actually. Helicopter rotor wash is enough downforce relative wind to blow a helicopter or to blow an airplane up into flight if they're not tied down properly. If an airplane is not tied down properly, a big gust of wind can pick that airplane up and it will actually fly. The relative wind over the airfoil is so effective that it will actually take off without there being any power or thrust generated from the engine. And that's basically like a kite or like a bird, essentially, right at that point. So from here, I would go into induced flow. I would talk about pitch angles. I would talk about ETL. I would talk about a resultant relative wind, more into the chord line. I would talk about tail rotor thrust. I would talk about tail rotor kind of concepts, dissymmetry of lift, etc. I'm not going to go into all that now, but that's essentially that's basically that's my presentation for tonight. I just wanted to talk a little bit about really what it is that makes something fly. So that's my presentation. And I'll leave it up if anybody wants to kind of comment on that or pitch in and talk about another topic. Now's a good time. I think you're muted, Jay, or I am. I'm not sure. I can't hear you, Jay, for some reason. Let's see. You guys could hear me, right?
Yeah, we could hear you just fine. Can't hear Jay.
Yeah, can't hear Jay. It would have been a bummer if I sat there the whole time talking and... Okay,
we're all just really good at lip reading.
Yeah, exactly. You're like, I kind of see what he's saying in those. I don't know, Jay. I don't know. Still nothing yet. I see you have your headset on. What? Oh, man. Uh-oh. Technical difficulties. I'm really curious about what you have to say. So I hope you can fix it. Until he pops on, does anybody have anything they want to say? Any comments? Any ideas of that approach to discussing the principles of flight for new helicopter students?
I came in late, but from what I saw, you did a really good job. That was nice.
Maybe you muted me when you muted Kit. Let me see. Unmuted you. Thank you for that. Yeah. No, you're up.
Yeah, Jay, you don't show muted on your name doesn't have the muted microphone next to it, so it's probably an input selection or something.
Yeah. You look good on my end from what I can see. I'll unmute you, Cricket, just in case there's something you wanted to say. You might have yourself muted, but yeah, thanks. Yeah, the concept here really, like I said, is just to try to kind of. Yes, I did hear you before, Jay. Mm-hmm. I don't know what that is. Let's see. There he is. I think we got
1 2 1 2.
Hey ho! I'll be. What do you know?
All right, I don't know why I changed there somehow, and the sun's coming through this window on my eyes, so I'm squinting, not because I don't understand, because this sun's on me. what I was trying to say was, great job. I really loved all the videos you used. I mean, that, for example, the hovering bird, as you said, forget about aerodynamics for a second. It's fascinating to watch. Yeah, it's really good, engaging videos, short videos. And I really like how you connected with, everyone's done it, right? As a child or as an adult, you put your hand out the car and you've changed the angle of attack of your hand without even realizing that's the terms you're using.
Right.
Yeah, great way of helping a student connect with all that stuff. And you talked about smoothing out the airframe with smoothing the rivets. You said about Howard Hughes. I was listening to a podcast about World War II, and there was a hurricane pilot in Battle of Britain, and he was smoothing out all his rivets, and he thought he got an extra 6 miles per hour on his speeds. Yeah, it's real. I mean,
that's amazing.
Talking about helicopter operations, you go to a heli base or anywhere there's a fire going on, and once the crews have finished for the day, if they're not doing anything, you'll see people cleaning down those blades. It makes a difference. It truly does. I may have told you this story before, John. We had an R-22 that came out of overhaul, and we just got a new person doing the painting, and they sprayed the blades. It was the second half of their 4,400 hours, and so they redid the blades, but they didn't do a great job, and there was kind of almost like a sandpaper texture on the blades. And as we tried to return this aircraft to service after overhaul, it was pulling about 2 inches more than it should have been, or the rest of the fleet compared. And that's what it was. They took the blades down, they smoothed them down, and then they repainted them, and that was it. It was no engine problem.
Wow.
It was 2 inches of manifold on just the smoothness of the blades. So yeah,
that's
just the surface of a lifting. One thing I was going to ask you about is, do you talk about the lift equation at all in this discussion of disposal of lift? As far as the lesson plan goes, or with the student.
Yeah, that's a good point. I had debated putting that in there, and I was gonna bring that in when I was talking about the Wright brothers, because they really did a lot of the mathematics to kind of help understand the lift equation further. So I mean, that seems like a logical spot. I don't know the lift equation. I was taught the lift equation. I've never applied the lift equation. I get the concept, but I think because I think it's a pretty standard thing to discuss, I should bring it in.
Well, it's tricky. I mean, so I teach helicopter fundamentals at college every term, and when we get to aerodynamics, we cover a lot of what you've been going through.
Mm-hmm.
And when you bring up the lift equation to a student, and I love math, but I'm not that great at it. But when I see an equation like that's the same as giving someone the far aim for the first time. It's not what I was.
Exactly.
So what I did is I took the lift equation and gave you a helicopter-friendly version of it. So you understand the concepts of lift and all the variables that are involved, but you pare it down to what can I as a helicopter pilot really change or pay attention to. I can show you that slide if you want. I can find it real quick.
Yeah, that'd be awesome. And I know a lot of you guys that are CFIs, have new students, and I'm just reflecting back to when I was a student, what my impression of trying to understand lift was, and I think my instructors went through the helicopter flying handbook and started kind of going through all the definitions and the presentation there, and I even read the helicopter flying handbook. I think it took me a lot longer to understand the concept than maybe others. I'm not sure, but I'm curious what some of you as CFIs, what some of the reactions you see from some of your students when you're first introducing them to something complex like this, that we actually break it down, try to make it as simple as possible, but still it's a complex subject. Especially James. James, if I may, James, I'm going to show your slide on as Diet Taco for you guys that are watching. I'm going to show you his. Do you mind?
Oh, hell yeah, go for it. Thank you.
Yeah, because it's really, really good. You should actually present it, because there's not a lot of Yeah, you use birds too. There's not. I mean, you are more of a visual.
Oh, I would love to. I'm playing Supreme Commander right now.
That's so awesome. All right, for those of you that can see my screen on the Vertical Lift Collective, James has all of his resources, all of his lesson plans, and they're really good, and they're uniquely James. They're not something you're gonna find in a typical presentation. And I was inspired by yours a little bit, brother, because it was so good. But he actually used a bird too. I forgot about that, but yeah, you're seeing it in action, and it does a really good job. I'm just going to kind of buzz through them real quick. These are all available for everybody who's on the Lift Collective. James has made them public, which is cool. I love all the different shapes of the airfoils you have here. Some videos.
In the early 60s, a
This is
Army
great
aviation
stuff.
was established at Edwards,
And we can
primarily
see
to
that, I
test
don't think.
helicopters.
Oh, you guys can't? Oh, shit. All right, I'm going to share my screen then. Yeah, that makes more sense. Thanks for saying that. All right, here we go. You guys have it now. There, you guys have it now? Yeah?
I see it. Yeah.
Okay, good. So, yeah, same thing, Bernoulli's principle. And I think, James, you made a lot of this stuff, but I love all the shapes of the airfoils here. This is a fun video. We can watch this really quick. I'm just going to turn it down.
60s,
Oh, I don't know. Maybe it's because I have it going in a couple places. I don't know what's going on. Anyway, we don't need to watch that video. But really good explanations of the angle of attack, how the chord line, the center of pressure works here, asymmetrical and symmetrical airfoils. Really cool. There's the symmetrical Robinson, the asymmetrical tail rotor, stalls, induced flow. This is where I would be going next. Really terrific stuff here. Parasite drag. If that's not parasite drag, I don't know what is. I haven't flown one of those yet, but I have been flying over water, so it'd be fun to get into one of those. Profile drag is a really great example. Induced drag, sure. There's our drag issues in action. There's our total drag curve. We borrowed the same slide from the handbook. Same stuff. So really just terrific approach to teaching this stuff. Get a lot of ideas from them. So you guys feel free to join the Vertical Lift Collective. It's an outstanding group. And yeah, I'll put in the link in the chat right now. But yeah, James has done a really good job with all those videos. So here's the link to the Vertical Lift.
I really like
Collective.
some of those animations too, James. Did you create it was like a blackboard style with white writing, and you had the translational lift and the pendulum effect. Those little animations, did you create those, or are they something you found?
I think he's deep into his game.
Commander.
sorry. I'm about to
Sorry,
this
man.
guy. It's pretty intense what I'm doing.
That's
Yeah,
right.
some of them I made. Some of them I stole. I mean, you guys know how it is.
Yeah. As long as it works, yeah.
Yeah. I don't know which one you're specifically talking about, but yeah, I probably
I'm sure it was
stole
yours.
That's so funny. All right, we're done with yours.
That's the Supreme Commander.
That's it.
Hey, John, one thing I did want to talk
Yeah.
about, when you were talking about asymmetrical and symmetrical airfoils. So there's a minor correction there, I would say, because the main rotor airfoil of the R22 and 44 being symmetrical, that's not standard, so pretty much everything I've flown other than a Robinson have a asymmetrical main rotor airfoil. My understanding is why they went symmetrical on that was it's cheaper, it's easier to make, right? But also when the angle of attack changes in a symmetrical, like the Robinson, the center of pressure doesn't really move very much.
Right.
And that means that there's not much control feedback forces that you get. But if you create a asymmetrical blade, then you get more lift efficiency, but you get these feedback forces. And so if you look at aircraft with hydraulics or trim assist, things like the Cabri or A-Stars, they're all asymmetrical main rotor blades. And so when you lower the collective of those, you talked about the idea about the brakes being on, and that when you lower collective of those, you go flat pitch, you're actually kind of negative pitch on the main rotor, so you're not bouncing up off the ground. So I think it's more about an engineering decision from Frank rather than the idea that helicopters can't have asymmetrical on the main rotor. I think Robinson is the exception. I don't know any other helicopter that has symmetrical main rotor.
Good. I'm going to amend my presentation then on that side. I want to be accurate. Did you say you have something to show?
Yeah, I wanted to show the lift equation thing and then how you can make it helicopter pilot friendly real quick. I have a whole slideshow of the whole fundamentals of aerodynamics, but that in particular, if you don't mind, I'll share that real quick.
Yeah, I'd love to see that. I'm also going to pull up the helicopter flying handbook where I about the asymmetrical airfoil and see if we can talk about that a little bit further too. Now I'm really curious.
Yeah, and I think we'll talk about the pros and cons and all that as well. So let's see. Let's try this window here.
While you guys are looking that up, it's interesting whenever you talk about Robinson, you're like, oh, why did they use that? Well, the answer is always because it's cheaper.
Or lighter, or simpler, or, yeah. Okay, I think I can make this work with you now, so let me just run this window. You guys see that? No?
Yes, we're streaming. We're seeing it.
Okay. Yep. So, you show this to most people that are getting into helicopters or aviation at all, and you might change your mind about wanting to be a pilot. But so, lift is coefficient of lift, which is really angle of attack and camber. We can't change camber. We can't change the shape of our airfoil. That's set. That would, in an airplane world, that would be extending a flap or a slat, but we can't change that. So that's out of our control. Angle of attack, of course, is our primary way of interacting with the helicopter as far as collective up and cyclic and stuff. The next piece is that weird letter that's rho or something. It means air density. And we can some degree change that. We choose whether we fly, middle of the afternoon in a summer's day where it's 7,000 DA, or we fly first thing in the morning. Maybe you can choose that, or whether you try to land at 8,000 feet or 2,000 feet. But the next piece I think is really important to point out is that velocity has that squared symbol on it. That is the most important change in the amount of lift you generate is the velocity of the airfoil. So keep that in mind, because you can apply this to so many things. All the aerodynamics from hover through to accelerating through all the different phases to V&E, all the you just start talking about like low RPM and things like that. There's many applications of this equation, and keeping in mind that velocity is a big deal. And then the last piece is surface area. So all these dots just mean multiplied by, and an S for surface area. The airfoil, we can't change the amount of surface area directly, but there are some little things that we can do. For example, if you take the instead of the airfoil individually, but the lifting area of the disc, if the disc is coning up, there's less lifting area. Or if there's more vortices being generated around the main rotor, that's reducing the effective lifting area. So then how do we talk about that as a helicopter pilot? So this is the lift equation for helicopter pilots. This is dumbed down to what we know and what we can control. So lift is really angle of attack times DA times RPM and airspeed. These are the things that we can have an effect on. Angle of attack I've already talked about was about collective, but it's not just that. Think about how in-ground effect versus out-ground effect, how the induced flow is changed. That's affecting the angle of attack, right? So we can choose to make an approach into ground effect or come to a high hover out-ground effect. That's going to be a massive difference in the amount of lift that the airfoil and the rotor disc as a whole can generate. The DA, we already sort of talked about choosing your time of day or the altitude that you want to go to. RPM, the main thing there is maintaining top of the green or whatever aircraft you're flying, and being really cognizant of low RPM and avoiding that situation. And that's your, throttle being the primary control on that. And then airspeed, that's everything. That should really be underlined, because airspeed, RPM and airspeed, those are the velocity squared again, right? Those are the really critical factors in lift generation. That's my little lift equation spiel. I shall unshare for a second.
Yeah, that puts it into perspective, a little bit easier to understand. That's for sure.
Equations don't go down well for many people that want to fly helicopters and put out fires. We don't want to have to deal with equations.
I know it, man. I certainly do not, and especially when you're early on learning all of the amount that you have to learn. Then you're throwing that in. You're like, I'm not. I just know. Do I have to? I remember saying that. Like, do I have to do this? Okay, I'm gonna share. From the helicopter flying handbook here. Where I got that information. And I had an idea. I had a kind of an epiphany, I recall, but I lost it. Where most light helicopters incorporate symmetrical airfoils in the main rotor blade. And I think my thought on that was because they're not powerful enough to generate, to have that velocity required to use an asymmetrical or non-symmetrical airfoil. I'm not sure.
I think it's because they don't have hydraulics.
Oh.
When it's talking about,
right.
I think that's what it is, because of the feedback forces.
Mm-hmm.
Because the center of pressure moves along the chord line, and then it will try to twist the rotor, and that will kind of be felt back through the controls. That's my understanding of it anyway.
So do you think my theory, or my explanation of a helicopter at zero angle of attack, if it did have a asymmetrical airfoil, it would want to push us into the ground, or it would want to start to spool up and take off? That is relevant, or does that not really apply here? Because that's kind of the only reason I thought the zero angle of attack made sense. So we don't.
Well, I mean, no, I agree with the idea that it produces lift at zero angle of attack, but with the collective rigging, you would just lower, and it would rig it to go below, so that you're not creating any. You don't want to. I'll give you an example, right? So we fly the 206 for turbine transition training, and we do that as part of our course. And so we get these guys come do about 10, 12 hours in the turbine, and we talk about all the many differences of flying turbine aircraft. And one of the key differences is that the hydraulics are set up differently than the R44. So those of you that have flown an R44 know that when you turn the hydraulics off for the hydraulic test, you do an X pattern to make sure there's no binding or restrictions that have been hidden by the hydraulics, and then you turn the hydraulics back on. You never test the collective. On the Bell 206, the way that the servos are set up and the way that the collective mixer is set up is that you have to, it's done differently, so that you have to actually check the collective, because it has its own servo, right? You have to check the collective and move freely. So you do this little 1-inch lift of the collective, hydraulics off. And of course, if it was generating lift, that would be a pretty dangerous place to even start at.
Right.
But there's either. Actually, I'll tell you one more thing before I go into like the A-Star and all these other aircraft and their different airfoils. Even when you are flat pitch in an R22 or an R44, I bet you've seen some movement of vegetation around you on and off airport, even when you got flat pitch. So there's some interaction. There's something going on. It may not be a full lifting stuff going on, but I feel like the all these other aircraft I've flown, they're not producing any lift when you collective all the way down. In fact, they're producing enough negativity. I think about when I do hydraulics off testing in the 206, that you can start getting this really unusual hop when you have the collective all the way down, and you actually have to bring it up a little bit to kind of equalize, so the aircraft's not trying to dig itself into the ground through these little hops that it's doing.
Yeah, so that makes me think about blade twist, right? Because there's different angles of attack in different portions of the blade, right? So yeah, I imagine at times there is negative angle of attack on a asymmetrical airfoil. That would lead to that type of scenario, right?
Yeah, that's again, John. That's great insight. You this is the great thing about this discussion group is between all of us, we bring up ideas that people have never thought of before. I really like that idea. That's exactly what's probably happening. Is there's an unequal lift across the rotor. At some point, there's negative, and some point there's equal, and some point there's probably a little bit of lift, and that might be why we're seeing vegetation moving, even when the collective's all the way down. Things like that. Great ideas.
Yeah, good stuff. Good stuff. It's fun talking about this stuff with you guys. Certainly do like it. Anybody have any comments on any of that? Anybody else want to chime in on anything? We don't have to run this study group very long if we don't have to keep it going if we're starting to wind down here. Jake, are you still on for next week, you think? Or I know I asked you earlier, but you think that's possible?
We were talking about what we were going to do. I can't remember. Remind me.
It was going to be high density altitude kind of summer prep flights that you do at your altitude with your students in the summer.
Yeah, I think so. I was going to try and put some slides together, but I teach it every summer to our. Actually, every time we hire people, I go through it with them a little bit. So the content's there. I just was thinking about trying to put some visuals together, but yeah, we can definitely do that.
Do you have a preference on the day, Thursday or Friday?
Let me get back to you about that.
Sure. Yeah. When you let me know, I'll make the event.
And you might have to chase me up on that because I got a few things going on with it. We're opening up a tower at our airport. And I got a bunch of meetings going on with the tower guys and the FAA about how we're gonna try to keep doing our helicopter thing with the tower opening up. So it's gonna be interesting.
Are you guys gonna be an echo to the ground, or are you gonna be a delta? A tower.
So we're
echo?
currently, So we're going to be delta to the ground part time, whatever the normal tower hours are going to be. But it's interesting because we're one of the busiest. We're in the top 3 busiest airports in the state of Oregon, but we don't have a tower. So we've been dealing with the chaos and the wild west of.
I believe it.
Making it work. And
I've seen your videos.
Now we're going to try to, make it work with a tower, and fingers crossed. But at the end of the day, it's going to make it safer, so that's great.
Yeah.
We want to try to keep some efficiency, so some discussions to be had there.
And it's going to give your students a big advantage in working in towered airports. I flew with James' guys over at Rogue Aviation in some busy airspace in California. That was that was outstanding training, and I can only imagine coming up into that. Yeah. Coming up through that.
That's an extreme version of tower operations.
Yeah.
That is, that's a great experience. You got that.
Yeah, I mean, we're Southwest is parking at their gate, and we're dropping auto rotations like right over top of them, and they're like splitting lampposts, and we're coming like right between them. I'm like, okay, that's just how you do it. Because I mean, we'll be out there flying in these Gulf airspaces, untowered. And instructors are like, don't fly over the buildings. Don't fly too close to blah, blah, blah. And it's like when you get in California, you just have no choice. I mean, you're flying over buildings. You're flying over everything. It's just unbelievable.
Yeah, metro flying is a whole different thing.
Sure is.
One more thing I'd say real quick about the aerodynamics is I would challenge you as an instructor or a student when it comes to aerodynamics. A really good, I didn't come up with this, someone, I can't remember who I can credit this to, but someone a long, long time ago said to me, tell a story with a whiteboard, just go up on a whiteboard or a pad and be able to tell a story from a hover in a no wind or picking up to a hover in no wind and then transitioning forward on a takeoff roll and then proceed all the way to V&E. If you can tell that story and drawing diagrams and all the things that are going on, that is a great way to prepare for either teaching it or for a check ride about knowing all the aerodynamics of a helicopter. Because you hit a huge amount of it, other than the EPs, the hazards, and the autos. If you can tell that story from 0 to 90 knots, whatever it is, I think that's a good challenge to set yourself, or you and your study partner.
That's a great one. There's that classic image that we have in that a lot of pilots share from the helicopter going through that process, and I'm going to put that on my screen right now. So we've all seen this, right? And I think this comes from the Helicopter Flying Handbook, but that's a really good example, right, of what you're talking about. From hover transition, ETL, transverse flow into ETL, and then into V&E beyond that. And I think there's another image that actually shows V&E. I think that's the retreating blade style.
That must have been someone who made that.
Yeah, maybe somebody did make that, but there's I think it goes all the way into like the retreating blade style. That might actually be mentioned in this slide, but yeah, pretty cool. And then obviously a handy little tool to kind of show that whole process too. These are great. Yeah, so I think that that's a good idea. Maybe on my after I get through the symmetry of lift and tail rotor thrust, induced flow, and all those other elements, that might be a good analogy and just kind of a good walkthrough of like, hey, let's put it all together, right? Yeah, that's a long lesson. It's got to be broken up into multiple lessons.
Yeah, aerodynamics is. Yeah, I managed to go from. I think I take 3 hours in a college class to go from. What do we cover? We cover three axes, to know how the aircraft moves around. We talk about torque reaction, some basic aerodynamic terms. So we label the airfoil and the aircraft, the blade tip path, and things like that. And then we start talking about all the different types of relative wind. Then we start drawing out vectors on an airfoil and showing induced flow and drag, main forces, lift generation. I mean, drag itself. That you did a great job of going through all the different types of drag.
Yeah.
And then we get into blade twist, translational lift, and on it goes. And where it ends, really, we don't do any hazardous stuff in that first aerodynamics, but where it kind of ends is, going through dissymmetry of lift and how that's dealt with, turns, load factor, and then let me show you something real quick. Can I share this with you real quick? Yeah. This is what makes people's eyes pop out of their head. Yeah.
Well, as you were saying all those things, they're just all like, I'm being reminded of all of us. Like, oh yeah, yep. Gotta talk about that. Just so much. All right, you're. I'm sure. Yep, there you go. You're up and running here. Yep.
Okay. So I showed them this, and they're like, "What?" And I'm joking because we're not gonna just look at this and try and break it down, as we see it. So we go into just the basic parts of the airfoil through. Yeah, that's a lot. You see, the Helicopter Flying Handbook has similar version, but it has like 4 airfoils, and I try to explain to the students, you don't need to memorize this. Okay, right. You just need to understand that you are controlling this driving region with the collective. But I've done some exaggerated versions. We kind of walk through it slowly. But this is the end of 3 hours. They're done. They're done.
No doubt about it.
Yeah, I was just gonna say, John, you asked like how most students react, and I think first time you talk about it, you do have this like deer in a headlight kind of look. But I thought as well, you presented it well, and yes, usually smaller pieces, and then break it up just like you said. So I agree with that. And then I was just going to add too, a lot of times, where I will introduce that lift equation as well is when you talk about dissymmetry of lift, and I'll just use like the velocity squared part just to start to introduce, right, that lift equation. I don't know, like I think the helicopter flying handbook has where they talk about like that tip speed. They'll talk about the advancing side being, like 500 knots versus the retreating side is that 300 knots. And then usually I'll just show students if you square that, that's part of that lift, that lift equation. So I usually introduce that lift equation in just small pieces, but again, not because I'm expecting them to memorize it or know, the physics of it. But that's another place too that you can introduce it, is when you're talking about dissymmetry of lift.
That's
but
good point. I'm gonna pull up the.
Does that make sense? Yeah, because we'll sometimes talk about like that tip speed. They talk about the advancing side. Because I do think in the R22, it is actually like 413 knots. But I think the helicopter flying handbook shows it as 400 knots, then you're adding like the 100 knots there's going. But I will just use that on occasion and just be like, so here's why it isn't just the difference between 300 or 500 knots. It's because it's velocity squared. So your difference is squared, which is a huge difference in speed.
Yeah, actually looking through I have the helicopter flying handbook up right now, and it's reflecting exactly what you're saying. That's good.
Right, and so that way it's just a piece of it at least, so I don't just again get that deer in the headlight look where you're just like, here's the lift equation. Do you get it? And they're like,
yeah, no.
No, and I was gonna. So Jay, you must be at Leading Edge. I think I'm up in Washington, and I had a student that started with me, and then I think he actually came down to Leading Edge and wanted to do, because you're 141, correct?
For most of the ratings, yeah.
Yep. Yeah. So I get updates from him every once in a while, and he has great things to say. So.
Oh, God, that's great to hear.
That's great.
Yeah, that's good to know. I just shared a slide here real quick, which is exactly what you were just talking about. I don't know if that's working, but the whole 400 knots, this is probably pulled originally from the same source that you were talking about. And then we're relating it back to the lift equation, because I keep relaying it back. I relate all these back to the lift equation, and they realize it's not as bad as it sounds. There is a purpose to this. There are some things to pull out of this. We see there's more lift because there's more velocity. Then we talk about flapping, and then we talk about how, if we're changing the angle of attack, we're now affecting the we're modifying the lift equation from the advancing and the retreating side, just like you said, the velocity squared on one part, but we're messing around with the CL or the angle of attack on the other side. But yeah, well, I'm glad.
I think the only other thing too that you mentioned, John, was just when you mentioned that LD max.
Yeah.
I don't. For me, the most detail I really go in is right. It's just, this is your lift to drag max where it's most efficient. I don't usually go into much more detail than that, right? And just letting them know that R22 is why we climb at 53, or the R44 why we climb at that 55. Why we have that center line basically of all three of those drags where they meet.
Yeah,
and but that's about it.
Yeah, and that's what I was looking for clarification on. That that VY at 55 knots really is that example of the LD max, essentially, right? Yeah. Okay.
Right. Yeah, that's my understanding.
Yeah.
Yes.
It's just not written that way in the POH, which I had to kind of dig around a little bit to try to figure out what the equivalent is.
I got information, and I don't know if you've actually done the Robinson safety course.
Yeah, I have. Yeah.
Okay, that's the first place where I actually saw it, where they truly wrote LD max and on that line. But that you're right. That's about the only place I've ever seen that.
Interesting. Yeah, it's just not as relevant, I guess, as in an airplane.
But it is for. Go ahead.
I'm driving, so I shouldn't be driving and videoing, but I'm going to lose service here. So I'm going to sign off, but hopefully I can see another one if it's on a Thursday.
Yeah, absolutely. We shift between Thursdays and Fridays. It was a pleasure having you. Thanks for joining.
All right. Thank you. I appreciate it.
It's like,
See you next time. Could be worse. It could be Supreme Commander.
Supreme Commander.
I always apply it back to the climb rate and also the minimum rate of descent on an rotor. What's the most efficient rotor? And then you can also put it into a scenario. You're coming into a towered airport. They say, "Hey, stay clear. I'll get back to you." So you're trying to preserve fuel.
Yeah.
What's the most efficient fuel burn? Or you're on station doing photo work or whatever it is. Knowing that most efficient rotor speed to burn the least amount of fuel.
And that's at 55 knots, essentially, right?
Yeah, 55 for the R44 and 53 for the 22. Yeah.
I just have briefly this kind of stalled, driving, and driven region, just similar to what you had. This just from the helicopter flying handbook here. Yours is a little more interactive than what I'm showing here, but it's essentially the same concept. How the angle of attack, induced flow changes on different portions of the rotor disc.
So this is the one from the helicopter flying handbook, right, John?
Yes, sir.
The reason I don't use the exact cut from the helicopter flying handbook partly is to reveal the information, partly so you can walk through the details, but they show the equilibrium, and I can't find reason to show the equilibrium. Like, to me,
right,
I want to tell you all about the driven and the driving and the use of the stall region. The point of equilibrium at B and D, I feel like that it just adds more to look at without any value in terms of like what is it actually doing? What doesn't matter, it's the equilibrium. That's why I try to like dumb it down a little bit and exaggerate some of these lines and stuff.
Right. Yeah, your exaggerations made it just seemed like it was easier to comprehend too. For sure. It's fun digging into this stuff though.
Yeah, I love aerodynamics. So, yeah, systems and aerodynamics. That's my thing, not weather. I like regulations too, but everyone has their thing, right?
Yeah, not weather. That's funny. I don't know a lot of people. It's like people dislike the weather portion. It seems like the most. A lot of guys I've flown with are just like, oh man, no weather. I don't care about the clouds. Those are,
I think part of the problem for a helicopter pilot in training is that we're being forced to learn a lot of stuff that doesn't really apply to us. This pilot weather is a lot of it is thousands. I remember taking some written tests where they're asking me as a helicopter pilot questions about clear air turbulence,
right? Which
is, we're talking jet stream.
Yes.
How did the FAA not get someone involved on those questions? They're like, hey, wait, I don't think the helicopter pilot needs to know about this. Is that kind of stuff, or we also don't go long range, right? So we're not looking at the country. We're not trying to go from East Coast to West Coast. We're looking at stuff much more within, fuel, a bag of fuel, which is maybe a couple of hours. It's 120 knots. How far is that? A state. We should be looking at statewide. That's one of the things that I think turns helicopter pilots off a little bit. Is it doesn't seem to apply to what I do on a day-to-day basis.
That's a really good point. I never really thought, why is it that they're teaching us this when it doesn't really apply? I just, but that's a really, because I mean that was a frustrating section for me that I know I spent a lot of time on to bring my knowledge back up after coming from a geology minor in college. I had all this information, but I lost a lot of it over the years. And so like the penguins on the iceberg analogy, right? All these other things came in, and my knowledge of kind of weather systems fell off the back of that iceberg. But it was stressing me out. And my DP or my instructors would always say, yeah, you got to know, where weather air masses are, and you need to know which air masses they are and what happens when two air masses converge. And, and you're just like, damn, man, what do I need to know about polar vortexes for?
Was that an opposing bases reference, by the way, with the Penguins?
Sure was.
Yeah, it's very good.
Sure was. Yep. And Seth Lake actually adopted it too. I don't know if you guys listen to Seth Lake, but he's really good. I'm going through the FOI right now, and he's walking me through the first part, task or area of operation 1, behavioral stuff, FOI. I'm going to take that test before the month's out, hopefully. Well, I'll probably be getting it next month. So, and then, CFI test. So just cranking through it.
I would give one piece of advice I would give to anyone studying FOIs right now is as you go through that book and you're trying to learn, and perhaps your instructor gave you a cheat sheet with these memory aids of letters and things to spell out these different concepts as memory aids, that's great, and you're going to learn it and you're going to be able to go into your written test and do well. But your oral check ride is going to be much more situational and scenario based. So as you go through your study notes and you look at each of these concepts, try your best to imagine a situation and write yourself a little mini scenario that applies to each one of those. And it's really hard because you've not taught perhaps anyone before, and you have to kind of be imaginative with it and maybe speak to your instructors. And can you give an example of how this would actually appear? But that's how it's going to be delivered on the check ride. It's going to be much more. I don't care if you memorize this mnemonic. I'm not going to ask you the mnemonic. I'm going to tell you a scenario. And I'm going to ask you, what is this? Or I'm going to say, give me an example of, as an instructor, and how would you deal with it? So I always thought about doing little flashcards where I would have, Johnny says this, this, and this. What is it? You'd have a little picture of Johnny drawn out in a little pen, and you turn over and like, oh, Johnny's being this, that, and the other, and I should do this, that, and the other. Right. I think it's the way to think about it other than passing the written test. It's a pretty hard written test, so good luck with it.
Okay. Yeah. Damn. Great. Thanks. I just cracked Shepherd Air on it, and I haven't really tried anything yet, but I'm gonna power through.
That's the way to go. Yeah. Good job.
Yeah. Thanks. Yep. Looking forward to it. Just chugging along at my own pace, and everybody's pace is good. Whatever you decide is good for you. Cool. Well, unless anybody else has anything they want to add, I think we're probably ready to wrap it up. Anybody? Okay, that's what I thought. If you guys haven't noticed this hat.
Yeah, I was going to say, nice hat. That was the last thing I was going to say. Nice hat. I saw it.
Triana and I kind of talked about it. We made one up. I want to get one out to everybody in the study group. So if you want one, we'll start making them and start getting them out to you guys. Just proud to have everybody here and really enthusiastic about the community we're developing. So thanks, everybody. With that, we'll wrap up Helicopter Study Group number 18. Next week, number 19, Jay's going to talk to us about HDA and some of the summer things we want to consider when summer flying in these smaller helicopters, power limited helicopters. So thanks, everybody. Thanks, Jay. See you guys.
Thanks, John. Thanks, everyone.
Bye.
Thanks. See you, bye.